Good afternoon, everyone. My name is Eric van Oort. I'm a professor at the University of Texas at Austin. I'll give you an update on what has been happening in terms of offshore drilling. So the agenda we'll go through in 15 minutes or less are the industry efforts post Macondo and the Deepwater Horizon event. We'll talk a little bit about the new BSEE well control rule, and I'd like to show you what the challenges are right now in offshore Gulf of Mexico well construction. And it's actually a very exciting time with regard to that, because there's some new technology on the horizon that can really help us, and I'm going to show you some of this as well. And then I'll end with giving you a go-forward view. So to start out, industry efforts after Macondo, there have been many. And the industry, I think, needs to be given credit, particularly for coming together and collaboratively working on a number of solutions. The industry has created an industry-wide well control incident database, has developed a task force for blowout preventer reliability and blowout modifications. Blowout preventers, of course, being these devices that can shut in a well in case of a well control event. Two well containment companies have been created, again with help from operators kind of banding together. Well containment is where you shut in a well that has gone out of control, and the image that you see on the right is a subsea capping stack, and a similar device was used to bring the Macondo well under control. Lots of work on the developments of standards for well design and operations management. I won't go through the entire list. You will have access to the slide pack later on, but other highlights is that there's been a mutual aid agreement and framework to enable operators to access additional resources in case of major oil spills, for instance. This all has placed us in a much better position to deal with another Macondo type event. We are much more able to respond quickly and work on wells that would blow out. The only criticism that I have from my side is that a lot of work has been done on the recovery side, on the kind of after the fact side. I think the industry, and I think the industry realizes this, more work need to be done on the upfront side to actually help prevent blowouts in the future. And the industry is now looking at SEMS, which is Safety Emergency Management Systems, on further training and certification of their staff, addressing human factors, and in particular addressing some technical issues which have to do with cementing of wells and zonal isolation, as well as real-time monitoring. And I'll come back to that a little bit later in my presentation. From the regulator side, BSEE introduced the new well control rule at mid-April. So we're about 2 months into this new control, and compliance is necessary 90 days after publication. So will be mid-July when operator compliance is required. It addresses and implements many recommendations from various investigations into the Deepwater Horizon and Macondo incident, including discussions that were held as part of the Offshore Energy Safety Institute forums, of which I was a part. It focuses on improving offshore safety through BOP and well control requirements, requirements for these BOPs to make them safer, to guarantee their uptime, to guarantee their operation under various conditions. It incorporates several industry standards. A very important standard is API Standard 53, and it also revises existing regulation, particularly 30 CFR 250, which deals with oil and gas drilling operations. And there are many reforms in the areas of well design and construction, well control, etc. The overarching theme of all of this is a focus on barriers. A barrier is anything, any system that prevents uncontrolled flow of hydrocarbons to surface. Those could be fluid columns with their hydrostatic head. There could be casings, cementing layers, BOPs. All of those are barriers. And BSEE has laid down criteria for barrier design and fabrication, construction, verification and testing, ultimately real-time monitoring, etc. So operators are currently busy to make sure that they are in compliance with this new well control rule, and we'll have to, of course, evaluate the well control rule further and look at its implications. And again, I'll come back to that a little bit further down in my presentation. For those of you that are not familiar with drilling, what we drillers do is we basically build inverted telescopes into the earth, basically conduits that we could use for gathering information and ultimately for producing hydrocarbons. So if you think of an old-fashioned telescope with its various segments, if you invert this telescope, that's what you have in a well. These segments, which are casing strings that are supported by cement, going to smaller and smaller diameters, deeper and deeper into the earth to the zones of interest. And if you would look down on a well like this, if you would place an eye on top of the well and you would look down, you would see what you see in the image on the right. You would see these concentric rings, which are the casing strings. The gray is the steel, the orange is the connections, and the white space are basically the spaces in between the casing strings, and you can see those are very narrow clearances. Those are the clearances in which we have to get cement in order to isolate various zones. So you can see that this is quite a complex thing. A deepwater well is a highly complex construction. Over the years, there has been an evolution in offshore deepwater well design. When we first went out into the deep water, using the very simple systems that Buford described, we had the well design that you see on the left. These basically drawn lines with the triangles on them are casing strings, and a casing design that you see on the left is reminiscent of what we might still see onshore. But over the years we've gone deeper into higher pressured environments, higher temperatures, and we have gone to these deep water tight clearance casing designs that you see on the right. And you see we've gone to a lot more casing strings. If you count them, you'll find 9 casing strings in order to get to depth. And with this, of course, the complexity and the risks associated have gone up. A good example is Macondo itself. This is the Macondo well design. Again, you see these dark lines with their triangles. Those are those casing strings that are set at various depths, mainly determined by the pressures in the earth. And if you count them, you'll see that Macondo essentially had those 9 casing strings to get to the target, to the zone of interest. The challenge for deepwater well construction is only increasing. I'll highlight 2 challenges which I think are particularly important. First of all, we've discovered some new plays in the Gulf of Mexico, particularly the lower tertiary and the Norphlet in the eastern Gulf of Mexico. The lower tertiary is something that we know from onshore drilling. It's this pink zone that you see in the picture on the top right. We find it in the offshore as well. We find it on the shelf at places like the Davy Jones complex, and then deeper in deep water at depths beyond 30,000 feet vertical depth into the earth. And there have been very significant discoveries. You probably have heard of the names of Tiber and Kashkida, Tahiti, Noddy Head, and so on. So significant opportunity for hydrocarbon production, but these are not easy wells to drill. These wells go 30 to 35,000 feet straight down into the Gulf of Mexico and actually are approaching what is the world record well that was drilled vertically into the earth, which was the Kola deep hole in Russia, which went in 40,000 feet. But I hope you see that these are very, very complex wells that are being constructed in order to address this particular opportunity. The other challenge is drilling into mature plays. Those are plays from which previously hydrocarbons have been produced and where there is depletion of hydrocarbon zones. I've given an example here of the Mars prospect that is being explored and developed by Shell. Shell has been at Mars for many years and has successfully produced from these sands that you see in this graph on the left. The colors there represent hydrocarbon sands that actually have been given names of colors. So you have the yellow sand, the green sand, the pink sand, the magenta sand. It's not that these sands actually have these colors, but that's the way they're designated. Shell has been producing from these wells for many, many years, but it now has found some deeper horizons at a near field called Mars B or Olympus, and it now has to drill new wells through these depleted zones to access these virgin pressured deeper horizons. And that creates some significant challenges to well construction. And I'll show you this on the next graph. On this graph, you see on the left what a traditional Mars well used to look like. A fairly simple and straightforward design. Now, because Shell has to drill deeper and go through these depleted zones, you see this well design has become a lot more complex. We in fact have 11 strings here to get to target. So these are some of the most complex wells drilled anywhere in the world. In fact, the Gulf of Mexico, what happens here in the US, sets the example for the rest of the globe. There are no more complex wells that are drilled anywhere in the world. And I'll show you what we're doing with respect to addressing this from a technology standpoint. One point that I wanted to make with respect to Arctic well construction. A lot has been said about Arctic well construction when the dialogue on it was going on with Shell, for instance, going to explore and develop in the Arctic. People were very much afraid of a repeat of the Macondo event in the Arctic. And I don't want to downplay the challenges associated with Arctic well construction. There are challenges associated with logistics. It's very difficult to work logistics in this very remote area. There are environmental concerns, and there are, of course, issues associated with local stakeholders that need to be addressed very seriously. But from strictly a drilling technicals perspective, from what we look at as drillers from the technical challenges, there's a world of difference. In the Deepwater Gulf of Mexico, you see on the right, we're drilling in very deep water, typically ranging from 3,000 to 10,000 feet, and we're drilling very deep into very high pressures. Here the depth shows as 20,000 feet, but as I've shown you, we're going to 30 to 35,000 feet. On the Alaska offshore shelf, typically you drill in tens of feet of water, and you go only several thousand feet deep into a normally pressured or near normally pressured environment. So the complexity between the two types of well construction is completely different, and the risk profile for the two is completely different. The offshore wells in the Arctic are more reminiscent of what we do on land operations. There is some new technology on the horizon to help us with these complex deep water wells. I wanted to discuss one with you called dual gradient drilling. The challenge that we have as drillers in drilling these wells is we have to manage the bottom hole pressures, the pressures that we have in the well, in between this red line and blue line that you see. Those are the pull pressure and the frac gradient. And this is what we call drill-in margin management. And in the picture on the right, you see that if we want to do this drilling margin management, we need, in this example, kind of 5 casing strings in order to get to target. You can count kind of these black lines with their triangles, right? Those are 5 wells to get to the target. And the reason we need 5 casing strings is because when we drill this well with a column of weighted fluid, we have kind of excess pressures at the sea floor, what we call the mud line. There's excess pressure, and we would like to get rid of that pressure. If we could do that, and you could do that with a technology called dual gradient drilling, then we have a much better ability to manage these downhole pressures, to get this downhole pressure in between this pore pressure and frac gradient, to do much more effective drilling margin management. And you see that in the picture on the right, on the left, we actually only need 3 casing strings to get to the bottom. And that's the benefit that you get with dual gradient drilling. And right now, there are 2 systems that are under development. The system on the left is a riser pumping system by a company called Enhanced Drilling. It's called EC Drill. What we do is we pump part of the riser, which connects the well to the rig through the column of water. We pump part of that riser dry, and that gives us this desired dual gradient drilling effect. The picture on the right shows a subsea pump that we have on the sea floor that pumps fluid back to the rig. This is the subsea mud lift system that is developed by a consortium that is led by Chevron. And these systems are currently being trialed, they're currently being matured. They are in the state of being really firmed up until they're commercially available. And when they're fully proved up, what we can actually think about is a reversal of this complexification trend in well construction that we've seen. We can even think about going back to those much simpler deepwater well designs that we started out with their lower risk and lower complexity. And so I think this technology addresses not only cost and efficiency of deepwater well construction, but also safety. I think with this technology we can significantly improve the safety of offshore well construction. So exciting times for us working in technology. Last slide, kind of the go forward. What can you expect to see in the coming months with respect to offshore drilling and well construction? As I said, operators are busy with the implementation of and compliance with the new well control rule. They have 90 days to comply. There are later dates for specific compliance elements, such as specific equipment modifications and rig modifications that need to happen, as well as implementation of real-time monitoring. That's what this acronym RTM stands for. And of course, industry is trying to get their head around better understanding the implications and consequences of the rulemaking. There's a lot of conservatism built into the well control rule with respect to casing designs and drilling margin management, and we need to better understand what those consequences are. Both industry and the regulator will start to address issues that are not currently in the rulemaking, such as well control training and certification, really verification of the competency of offshore staff, addressing human factors, working on the safety emergency management systems, addressing zonal isolation, etc. And what I would argue for is that this requires really effective operator-regulator dialogue, a spirit of collaboration and cooperation rather than antagonism, polarization, and adversity. These issues are much better handled, and you get much better regulation if the regulator and the operators are working constructively together and there is some mutual trust between them. I myself am getting involved through the Offshore Energy Safety Institute with working with the regulator, working with BSEE to define and train their staff on real-time monitoring. So, and this will happen at the University of Texas at Austin. It's something we're very excited about. And then we will see us continue to address these new deepwater technological challenges, developing system practices and standards for these very deep wells that are drilled in high pressure, high temperature environments, looking at progressing these very promising technologies such as dual gradient drilling and managed pressure drilling, and then also trying to deliver standards and rulemaking for these new technologies in a timely fashion. Typically, it has taken historically about 10 years to develop a new API standard, but technology development is speeding up, and we have to also, of course, accelerate the timeline for standards development and implementation. So with that, I'll give it back to Cassie, and I will take questions from you later on.